In this illustration, we'll study about an extraneous charge at the dielectric boundary. Here we are given that a parallel plate capacitor is filled up with two dielectric layers 1 and 2 with thicknesses d1 and d2 and dielectric constant k1 and k2 and resistivities ρ1 and ρ2. A voltage V is applied to the capacitor with electric field directed from 1 to 2. Find the surface charge density of charges appearing at the boundary of dielectrics. Now in this situation, if we draw the capacitor for battery clarity, here this is the capacitor, and there are two dielectrics filled in it. They are having distance d1 and d2 with the dielectric constant k1 and k2, and the resistivity is ρ1 and ρ2. This will connect the battery EMF V, electromotive force voltage V. In this situation, we know this dielectric having resistivity. In this case, the capacitor will have leakage current, for which we can first calculate the resistance between plates, which can be given by the series combination of the resistance these two dielectors. And we consider here the plate area is equals to A. We know the resistance R equals rho L divided by A. I get this dielectric media resistance R1 and this R2. And the total resistance between these plates, throughout these plates, is equal R1 plus R2. Because these dielectrics are in series combination. Then we can write the resistance R1 equals ρ1 d1. The length is d1 divided by A. And R2 is ρ2 d2 divided by area A, plate area A. And the total resistance R equals R1 plus R2. As we are having resistance, a constant leakage current will flow as constant potential difference V is applied here throughout these parallel plates. So we can calculate the leakage current in capacitor, which can be given as V equals IR. So then I equals V divided by R. I equals V divided by R is here. Common A ρ1 d1 plus ρ2 d2. So on substitute in the value, we can see this is I equals VA by ρ1 d1 plus ρ2 d2. This current flowing between the two plates. Now we wish to find out the surface charge density of charges appearing on this boundary. Here we can split these capacitors and two capacitors series in here. I split these two capacitors. I consider these two capacitors are connected in series. This is C1 and this is C2, and they are connected across the battery of electromotive force V. Then also here we can see current I is flowing constantly throughout the system. But in this particular case, on the two plates connected with the capacitor, of the charges will not be the same. So here we can write down the value of the charges appearing on these capacitors is plus Q1 minus Q1 and plus Q2 minus Q2. There was different charges series capacitors. Here we can find out the charges on plates. Here we can consider this plate is X and this plate is Y. Now the charges at plate X and Y. So charge on plate X we can write it is minus Q1 of the value equals C1 multiplied by the potential difference across this capacitor. I got potential difference across C1 equals V1. Potential difference across C2 equals V2. So then I can say Q1 equals C1 V1. We know the capacitance value of parallel plate capacitor C, capacity C equals K epsilon naught A divided by D. So value of C1 we can write as K1 epsilon naught A divided by D1 multiplied by potential difference across the capacitor C1. It is V1. Okay, V1. This current flows I. So I can say V1 equals IR1 because the C1 capacitor has the resistor R1 and C2 also have resistance R2. Then I can write V1 equals IR1 and V2 equals IR2. I is the leakage current. So V1 value can be written as IR1 multiplied by I. I is there. VA by rho 1 D1 plus rho 2 D2 multiplied by resistance of this leaky capacitor. Its resistor is R1. R1 is there multiplied by rho 1 D1 divided by A. So in this situation we can see this D1 gets cancelled out and A also gets cancelled out. And the value of Q1 we are getting is negative of there was rho 1 K1 epsilon naught A V. Rho 1 K1 epsilon naught V A divided by rho 1 D1 plus rho 2 D2. Similarly, charge on capacitor C2 on plate Y have charge plus Q2. We can written as C2 V1. So C2 is K2 epsilon naught A divided by D2. K2 epsilon naught A divided by D2 multiplied by the potential difference V2 across the capacitor C2. Okay, the voltage V2 we can written as IR2. I, which is again written as VA divided by rho 1 D1 plus rho 2 D2. This is I and the R2 is the resistance of capacitor C2. R2 is there. Rho 2 D2 divided by A. So here D2 by A gets cancelled out. And simplifying this will give us the value of Q2. Here we can see rho 2 K2 epsilon naught VA divided by rho 1 D1 plus rho 2 D2. rho 2 K2 epsilon naught VA divided by rho 1 D1 plus rho 2 D2. So we wish to calculate the charge density on this boundary. We can calculate. Now we can incombine the total charge on this boundary. This X plate has minus Q1 charge and this Y plate has Q2 plus Q2 charge. And the total I can written as sum of these charges. Q total equals common factor epsilon naught VA divided by rho 1 D1 plus rho 2 D2. And there was rho 1 K1 but minus rho 1 K1. First I write this rho 2 K2 minus rho 1 K1. Now we need to calculate surface charge density of charges appearing at the boundary of dielectrics. Yes, we can find surface charge density. It equals total charge divided by surface area. Consider there was one surface area, it is A. Then the total charge is there, epsilon naught VA divided by rho 1 D1 plus rho 2 D2, yeah, rho 2 K2 minus rho 1 K1. This is the total charge and divide is the surface area. There was one A. So surface density on boundary. So we substitute the value of this and A gets cancelled out. And the result we are getting is epsilon naught V multiplied by rho 2 K2 minus rho 1 K1 divided by rho 1 D1 plus rho 2 D2. This is the final result of this problem, which is considered the extraneous charge at the dielectric boundary of the two dielectrics on this situation.